Alright, so these first couple problems here are money problems, so we'll be using one of these two equations. If you're going to use this equation, you only want to use it when it says continuous, otherwise we use the compound interest equation. So this first problem says $1,000 is invested, so that's our starting amount, so that will be and then at 4% compounded quarterly after a period of 2 years. So there's no continuous, so we'll use this equation here. And our starting amount is P, our principal. This is our rate here. We'll rewrite that as a decimal. And then because it says quarterly, that means 4 times a year we'll calculate the interest. So N is 4. And then T is 2 for years. So we will be trying to find A. Plug in 1,000 for P. And 1 plus 0.04 divided by 4. All to the 4 times 2. Now, you can type it all into the calculator, but you have to make sure you put these two together. So I recommend multiplying those two together first. So you have 1,000, 1 plus 0.04 divided by 4 to the 8. And if you type that into your calculator, you should get the answer, 1,082.86. So for this problem over here, same thing. We don't see the word continuous, so we'll be using this equation here. And so you're going to say, okay, $600 is invested at 5% compounded daily after a period of 4 years. So 600 is our starting amount, A. 5% is our rate, so that'll be R is 0.05. It's compounded daily, so that means that we're going to do it every day. So that'll be 365 days a year over 3 years, so that'll be T. So we'll have A is equal to P, 1 plus 0.05 divided by 365 to the 365 times 3. So if you, again, make sure you multiply these together first or put parentheses around them when you're doing that. So you should type in 600, 1 plus 0.05 divided by 365. And then if you do multiply these together, you'll have 1,095. And if you type that into your calculator, you should get $697.09. This next problem does have the word continuously in it. So because it says continuously, we will use this equation here. $1,000 is invested at 10% compounded continuously. So 1,000 is our starting amount, P. I think on this last one I said A, but this should be a P. Starting amount P, this is our rate, we write it as a decimal. And it's continuous, and then the 4 years is our time. So we'll have A is equal to 1,000 e to the 0.10 times 4. Again, we're using this equation here. You can just type that into your calculator as long as you close the parentheses on both of those. And if you type that in, you should get 1,491.82. This next problem is asking us how many years will it take for an initial investment of $10,000 to earn $25,000. Assume the interest rate of 6% compounded continuously. So because it says continuously, we will be using this equation again. Anytime it's money problem, it's going to be one of these two. If it says continuously, you use the left. So our starting amount will be P, which is 10,000, and it's growing to 25,000. So that's our ending amount. Our interest rate is 0.06. and we're looking for how many years, so we're trying to find t. So we'll go ahead and plug this into our equation here, and we'll have 25,000 is our ending amount, 10,000 is our starting amount, e to the 0.06 times t. And we want to solve for t, so the first thing we'll do is we'll divide by 10,000. And that will give us 2.5 is equal to e to the 0.06. And then we'll ln both sides to get rid of the e. That will cancel out the ln e. And so then we'll have ln of 2.5 is equal to 0.06 t. And then the last step will be divide by 0.06. And if you type that into your calculator exactly as is, you should get t is equal to 15.3 years. It says round to the nearest tenth, so that's 1 decimal place. So we're rounding this spot and it stays at 3. All right, so now on to problem number 5. Again, a money problem, so we'll be using the same equations, and specifically this one says continuously, so we'll be using A is equal to P-E-R-T for this whole problem. It says, following the birth of twins, the grandparents deposited $16,000 into a college trust fund that earns 4.2% interest compounded continuously. Find a function for the amount in the account after t years. So we're going to write our equation here. Will be A. We don't know the ending amount. We have a starting amount of 16,000. Our interest rate 4.2 we'll write as 0.042 times t. So we want t and the amount to be in our equation. So that's our answer there. Now we can use that to solve the other 3 problems here. So we'll find the amount in the account after 12 years. So this is going to be plugging t equal to 12 into our equation. Type that into your calculator. Just make sure you close your parentheses after the 12. And you will get 26,485.27. Same thing here for this problem, but now we're plugging in 18. Don't forget to close your parentheses after the 18, and we'll get 34,075.84. Now for this question, we're asked how long will it take the investment to double? So what does it mean for the investment to double? Well, our investment is how much money we put into the account. So they deposited $1,600. So to double that will be $3,200. And we want to know how long. So we're looking for time. So we're going to plug in $3,200 for the ending amount. And t will leave in there. Now we have to solve. So first we'll divide by 16,000. And we'll get 2 is equal to e to the 0.042 t. Then we'll ln both sides. That will make the ln e go away. So we'll have ln of 2 is equal to 0.042 t. Divide by 0.042. and type that into your calculator, and you should get t is equal to 16.5, since it says round to the nearest tenth. Alright, so for this problem here, when I'm looking at this, I say cash Social Security distributions were 35 million or 0.035 billion in 1940. This amount has increased exponentially to 492 billion in 2004, assuming the exponential growth model applies. So this one's about money, but not about like putting money into an account. So we need to go look at our equations. And if we look at our equations here, we'll see when it's not about money, it's either going to be exponential growth or decay. And we could maybe use our decay rate, but this is just exponential growth. So we're just using this equation here. So if it's not about money, which this one is, but it's not about putting money into an account, we're going to use that equation. So we'll be using the equation P is equal to P0 e to the kt. So the first question asks us to find the growth rate K. So we'll start off with that. So P0 is our starting amount. And so that was this amount in 1940. That's when we started. And then in 2004, it was 492 billion. Now we want to use both the billions instead of this one because we want to keep it the same. So if we start with 0.035 billion, that will go for P0. This will be our ending amount P. We're trying to find K, and T will be how much time has passed. So that will be 2004 minus 1940, which will be 64 years. So we have to find K, so we'll plug in P0. Leave K, plug in T is 64, and then we'll plug in P as our ending amount. And then we'll go ahead and solve this equation. So I'll start by dividing by 0.035. So 492 divided by 0.035 is going to be 14057.14. 286. And this keeps going, so you can either do ... or if you want to round to 4 decimal places, that's okay. And then over here we'll have e to the k times 64. So then we'll ln both sides. That'll cancel out the e. Ln of that will be 9.5 5508. You can either leave the 4 decimal places or just keep that number. It doesn't really matter on these whether you do 4 or whether you go further in. Just keep the whole number. And then if we divide that by 64, we'll get K is equal to 0.14923. And if we're rounding to 3 decimal places, we want to keep this one the same because of the 2 after. So it'll just be 1.49. So that is our answer here, our growth rate, K. So then it asks in B to find an exponential growth function. So that's just going to be replacing P0 and and K. So we'll leave P. P0, our starting amount, is 0.035, and our K is that we just found is 0.149t. And that's positive because this is growth, so that's good that our K is positive. So for the next one, we can use this equation to solve the next couple questions. That's why we find it. So we'll estimate the total cash distributions in 1965. So the total cash distributions is the ending amount, P. That's what we're looking for. And we need to know what to plug in for T. Well, 1965, we're looking for the years since the beginning. So remember, 1940 was the beginning. So we're going to do 1965 minus 1940. and that will give us 25 years. So 25 years since we started. So we'll plug that in for t. And you can plug that into your calculator. Just make sure you close the parentheses after the 25. And you should get 1.45 if we round it 2 decimal places, and that's $1 billion. Then we want to know when the total cash distributions will reach 550 billion. So when is t? So now we're looking for t, and this is our p. So now we're going to plug. So we will plug in 550 for p. Our P0 is 0.035. And we're trying to find t, so we'll leave that. So we'll start by dividing by 0.035. And we'll get 15714.2857. You can keep the whole number, or you can stop at 4 decimal places. Either one will not cause any problems with these kind. We'll ln both sides. That will cancel out with the e. And then ln of that will be 9.6623. You can keep the whole decimal if you want. Then we'll divide by 1.149. And we'll get t is equal to 64.84. And if we round that to the nearest year, we'll round the 64 up to 65 because of the 8. All right, so now for this problem here, we're going to find the exponential growth function. And we know the world population was 6.8 billion in 2009, and the growth rate was this much. So this is not a compound interest problem, so we're going to be using the formula P is equal to P0 e to the kt. And first thing we have to do is find the exponential growth function, so we're going to find k. So we'll plug in, this is P0, our starting amount. This is P, we don't know what the ending amount, but we already know K. It is that percentage, that's the growth rate. So that would be, they actually give it to us for this one, so that'll be 0.113. So to write our exponential growth function, we'll have P, we'll fill in 6.8 billion in for P0, 0.0113, and then we leave T. Anytime we're writing an exponential growth function, you want to leave P and T. So then we'll use this equation to solve the next problem. So we're going to estimate the population of the world in 2020. Well, in 2020, our starting amount was in 2009. So in 2020, we are going to figure out how far away from 2009 we are. So 2020 minus 2009 will give us 11. So then we will plug that in for time. And you can just type that into your calculator. Just make sure you wait to close the parentheses until after the 11. And then you should get 7.7 billion. Now for part C, we're asked when will the world population be 8 billion? So now we know the population is 8 billion and we're looking for T. So this is going to be our ending amount P and we're looking for T. Again, we're using this equation now. So we're going to plug in 8 in for P. And we'll solve for T. So we'll start dividing by 6.8. If you want to round to 4 decimal places for now, you can. Or you can leave the number as is. Then we'll ln both sides. That will cancel out the ln e. So we'll take ln of our previous answer, or ln of the 4 decimal places that we have here. You'll get close enough an answer at the end. It doesn't really matter whether you round to 4 or more. So this will be 0.16246. And we'll have 0.0113t. So then the last step will be to divide both sides by 0.0113. So we'll get t is equal to 14.37 years, and it says round to the nearest year, so that will be t equals 14 years. All right, so for the next couple questions, these are all continuous compound questions. So we'll be using A is equal to PERT equation from your list of equations because it's continuously compound. So this first one here says that $35,000 is invested. So that will be our starting amount, P, that is compounded continuously. So we're using that equation, and this is our rate. So we move the decimal over 2 spots. And we want to know how much is in the account after 5 years. So this is our time. So we're looking for A. And we'll start with 35,000. E to the 0.032 times 5 years. And if you type that into your calculator correctly, don't forget to wait to close your parentheses until after the times 5. You should get $41,072.88. For number 8, we want to find out how long it will take the investment to double. So if we want to know when the investment doubles, we're looking at 35,000 times 2. So that'll be 70,000. So that will be our ending amount, A. So now, and we want to know how long, so we're looking for T. So we'll start with our ending amount, A, being 70,000. Starting amount always is 35,000. Rate is the same interest rate for the whole account, and now we're solving for T. So we'll start by dividing by 35,000. And we'll get 2. And then we'll ln both sides. That'll make the e go away. So you'll have ln of 2 is equal to 0.3032t. Divide by 0.032. And you get t is equal to 22 years when we round to the nearest year. For the next problem, it says $5,000 is invested in an account that is compounded continuously, so we're using the same equation. That's our starting amount, or our principal P. After 5 years, the account balance is $7,130.90. What is the interest rate? K. And 5 is our years, so that's time. So this is our ending amount. So we'll plug this into our equation. So we'll have our ending amount and we plug in 5 for T. We're looking for K. So we'll start by dividing by 5,000. we'll get 1.4261. We'll ln both sides. That'll get rid of the e. And then we'll divide by 5. So we'll have k is equal to ln of 1.4261 divided by 5. And so k will be 0.071. And it also says round to 3 decimal places and write as a percent. So as a percent, this will be 7.1%. We move the decimal over 2 spots. All right, part C says, after 5 years, you have $9,923.47 in your savings account that compounds continuously at a 5.6% interest rate. What is the initial investment? So now we're looking for P. This is our A, and this is our interest rate. So now we'll plug in this for our ending amount. We're looking for P. And it says after 5 years, so that'll be our T. And for this one, we can just type this into our calculator here. When we type that into our calculator, we'll get P times 1.3231. And then we'll divide by 1.3231. And we'll get P is equal to 7499.9972. And if we're rounding to the nearest cent, this 9 is going to go up because of the 7. So then this 9 will go up, and this 9 will go up, and this 9 will go up, and this will round to $77,500. All right, so for this problem, they gave us our equation, so that's pretty nice. We don't have to worry about what equation to use. And it says that the amount of radioactive bacteria in grams at time t in months, so t is the time in months. And so this guy is our amount of radioactive bacteria. And it says find the number of grams present in 3 years. So we want to find when t is 3. We're looking for y. So we're just going to plug that into our equation. And if you type that into your calculator, you should get 3,642.58 grams. And that's it. All right, so for this next question, this is a half-life problem. It's asking us for the decay rate K for these substances given their half-life. So if I know the half-life, this is when I get to use the half-life formula to find K. And remember, it's ln of 0.5 divided by t, where t is the half-life. So for this problem here, K would be ln of 0.5 divided by 3.1, because that's the half-life. So that will be negative 0.224. Note that this is a negative decay rate, which is good because it's a equation. And then if we were to write it as a percent, it'll be 22.4%. If you move the decimal back over 2 spots. So you could see it both ways. So for this one, K will be ln of 0.5 divided by 79. And so you'll get negative 0.009. If you write that as a percent, that would be 0.9% if you move the decimal over 2 spots. Okay, so A asks, if the substance has 75 grams of polonium, how long would it take for the amount to decay to 12 grams? So we're using our exponential growth and decay equation here because it's not a money problem about compound interest. And so we know that K for polonium, we just found that up here, is this guy right here, negative 0.224. So we'll use that for K. And then if we have 75 grams of polonium and it decays to 12 grams, we're looking for how long, so that's time. So this is our ending amount, this is our starting amount, and we'll plug that into our equation. So we'll have 12 grams is our ending amount because it's getting smaller. 75 grams is our starting amount. E, our K that we just found using the half-life formula, and we're looking for T. So the first thing we'll do is divide by 75. You'll get 0.16 is equal to e to the negative 0.224 t. Then we'll ln both sides. That cancels that out. And so then you'll have ln of 0.16 is equal to negative 0.224 t. So then the last step will be to divide. So you'll have ln of 1.16 divided by negative 0.224. And so you should get 8 years if you round to the nearest year. Then it says an artifact was found to have 85 grams of uranium, and then it was placed in a lab for 50 years. Now, how much uranium was present after 50 years? So uranium, we just found the K up here. And so it starts with 85, so that's P0. It was placed in a lab for 50 years, so that's T. And now we want to know how much. So we'll look for how much we have now, starting with 85. K is negative 0.009, and time is 50 years. Type that into your calculator, and you'll get 54.2 grams if you round to the nearest tenth. All right, this is a new problem here. The radioactive element carbon-14 has a half-life of 5,715 years. Analysis indicated that an artifact contained 76% of its original carbon-14 at the time it was found. So first we need to find K, because we don't know that for this problem. So we'll use our half-life formula. And we'll go ahead and round this to a few decimal places because it's a pretty small number. Okay, and so then when we go to plug into our equation, we're using P is equal to P0 e to the KT. We know K, and we don't know how much it started with, and we don't know how much it ended with. So this is one of those ones where we have to pick P0 to be something. So we'll pick P0 to be 1. And so then P will be 76% of that. So 0.76 times 1, which is 0.76. So then we'll plug that into our equation. So we'll have 0.76 is our ending amount, 1 is our starting amount, and then we'll have negative 0.0012 t, and we'll solve for t because we're looking at how old it is. So we'll start by dividing by 1. That's not going to really change much, so we'll still have 0.76 is equal to e to the negative 0.00012. I think I left out a 0 here. Then we'll ln both sides. And we'll have ln of 0.76 is equal to negative 0.00012 t. And we'll divide by negative 0.00012. And we'll get t is equal to 2,287 years old. Part B says a different artifact originally had 16 grams of carbon-14. present. How many grams of carbon-14 will be present in 4,500 years? So this is our time. This is now our starting amount, and we get to use the same K because it's still carbon-14. So we're looking for our ending amount. Our starting amount is 16. And we're going to see how it is after 4,500 years. So type that into your calculator, and you will get 9 grams. Alright, so in this problem here, the number N of farms in the United States has declined continually since 1950. In 1950, there were 5.6 million farms, and in 2008, that number has decreased to 2.2 million. Assume the number of farms decreased according to the exponential decay model. So we're going to use our exponential decay equation. First thing we're supposed to do is find the value of K. So we'll look at our starting amount, and that was 5.6 million farms, and our ending amount was P, 2.2 million. We're looking for K, and we have to find the time to plug into that. So if we end with 2.2, start with 5.6, and we're looking for K, we need something to plug in for T. And so we're looking at how much time passed. So the starting was in 1950, and 2008 was the ending. So 2008 minus 1950 will be 58 years. So T is 58. So then we'll solve. We'll divide by 5.6. We'll get 0.3928 is equal to e to the k times 58. And then we'll ln both sides. And then we'll have k 58 is equal to ln of 0.3928, and we'll divide by 58. And we'll get k is equal to negative 0.016. It says to round k to 3 decimal places. And then we'll write an exponential equation that describes the number of farms. So I'm going to have to do that off to the side here. So for the second part here, when it says write an exponential equation, remember you're going to plug in P0 and K whenever you're doing that. So we'll plug in our starting amount, which is 5.6, and our K that we just found. So now we'll use this equation to solve the next couple problems. So we want to estimate the number of farms in 2011. So we started in 1950. So how far is 2011 from that? That'll be 61 years. So we're looking for the number of farms in 2011. So this is our time, and we're looking for P. So we'll plug in 5.6 E, use our K from our equation up here, and we're plugging in 61 for T. Type that into your calculator, and you should get 2.11 million farms. And then it says at this decay rate, when will there only be 1 million farms? So this is our ending amount P, and we're asking for when, so now we're looking for time. So using the same equation up here, we want to know when it ends with 1. So we're looking for the time. So we'll divide by 5.6. That'll give us 0.1785. ln both sides. divide by negative 0.016. And you'll get 107.7 years. So now that's since 1950, so do 1950 plus 107.7, so we'll round that up to 108, and that is 2058. So this next question here, we are using the data for 2009 and 2013 to find the value of K and write an exponential function that describes the cost per watt. So we're going to use our exponential growth equation, and we're going to use the years 2009 and 2013. So our starting amount is in 2009, so that'll be 4.84. Our ending amount is in 2013, so that's 292. We're going to find K, and the years that happened between 2009 to 2013, you can subtract those, and you'll get 4. So if we're going to solve this equation, we'll divide by 4.84. And we'll get 0.603. 3 is equal to e to the k times 4. Then we'll ln both sides. And we'll have ln of 0.6033 equals k times 4, divide by 4. And you'll get k is equal to negative 0.126. So for our exponential function here, again, we'll just fill in p0 and k. So we'll have p is equal to, so your equation here will be p is equal to your starting amount, which is 4.84, e to the, here, we'll rewrite it down here. P is equal to 4.84 e, and then we'll use the k that we just found and leave a t in there. So this is the equation, the exponential function, and that's what you can use to solve the rest of the problems. So for problem B, we're going to estimate the cost per watt of electricity in 2015 and then in 2018. So in 2015, we need to figure out what t is. So we started in 2009. So 2009 to 2015 is 6 years. And then 2009 to 2018 is going to be 13 years. So these are two separate problems. So for 2015, we'll do p is equal to 4.84 e to the negative 0.126 times 6. And for 2018, we'll do p is equal to 4.84 e to the negative 0.126 times 13. And type these into your calculators, and you should get $2.27 and $1.65. So those are your two answers. And then part C says, at this decay rate, in which year will the average cost be 1.85? So now we're asking for P, and we want to know in which year, so we're looking for T. That's our P, and we want to find T. So we'll do 1.85 in for P. And we're trying to find T. So we'll start by dividing by 4.84. that'll give us 0.3822. Then we'll ln both sides. So we'll cancel out with the e. So we'll have ln of 0.3822 is equal to negative 0.126t. And then we'll divide both sides by negative 1.26. So we'll have t is equal to ln of 0.3822 divided by negative 0.126. So t should be 8 years, because it says round to the nearest year. All right, last question here. In a town whose population is 3,500, a disease creates an epidemic. The number of people n infected after t days, so n is the number of people infected, and t is days, after the disease has begun. And so they give us an equation for this one. This is the logistic growth equation. So if we want to know how many people are initially affected, we're talking about when t is equal to 0. So we'll plug t is equal to 0 and solve for n. And if you type that into your calculator, don't forget to put the bottom in parentheses. And if you type that into your calculator, you should get 167 people. We'll round to the nice whole number, because we don't want partial people. So you basically can ignore this. I mean, you can round your answer and then, but we don't want partial people. So then after 2 days, we'll plug in 2 for t. Type that into your calculator. Don't forget to put the bottom in parentheses. And you'll get 500 people. And then same thing for after 6 days. We'll plug in 6. And don't forget to put your bottom in parentheses, and you'll get 2,267 people. So then how long will it take for 3,000 people to be infected? Well, we'll put 3,000 in for n, and we're looking for time. So now we will do the switcheroo, where these two will switch spots, and we'll have 1 plus 19.9e to the negative 0.6t is equal to 3,500 or 3,500 divided by 3,000. So that will give us 1 plus 19.9e to the negative 0.6t is equal to 1.16. And I'm going to put a dot, dot, dot here. Remember, don't round in the middle of your problem here, or it will change your answer. So then we'll subtract 1 from each side. And then we'll divide by 19.9. ln both sides. Divide by negative 0.6. And we'll get 7.97. So we'll round to the nearest day here, and we'll get 8 days.